All right, let's dive into a really beautiful piece of geometry. We're going to look at a puzzle that hides this simple, super elegant secret right in plain sight. And it all kicks off with just one single drawing.
So check this out. What we're seeing here are three circles, right? Two big ones, one little one, and they're all just sitting on a straight line. Seems straightforward enough. But then there's this formula. What's the connection here? How on earth could this equation describe what we're looking at?
Well, the answer to our little puzzle actually has a name. It's Descartes' Theorem. And it's all about this wonderfully simple idea of kissing circles.
So what in the world are kissing circles? It's a charming name, right? But it's for a very specific geometric idea. It just means the circles are mutually tangent. They touch at one single point, and they don't overlap. Exactly like the circles in our drawing.
And get this idea has been captivating people for centuries. The brilliant philosopher and mathematician René Descartes, yeah, that Descartes, he first wrote about the theorem way back in 1643. But even today, it's so elegant that it's still inspiring new discoveries in both math and art.
Okay, so let's get right to the heart of it. We're going to break down that formula and finally reveal the secret of these kissing circles. And I promise you, it is way more intuitive than it looks.
Let's start with the two main players here. We've got our two big circles, and we're going to call their radii x and y, just like you see in the diagram. So far, so simple, right?
Now here comes the really clever part. The theorem doesn't actually use the radii themselves. No, instead it focuses on the inverse of their square roots. It's this unique relationship that is the key to this whole puzzle.
So why is that relationship so important? Well, because when you add those two values together, what you get perfectly predicts the size of that third, smaller circle, the one nestles right in between them. We'll go ahead and call its radius z.
And boom, there it is, the full equation. 1 over the square root of x plus 1 over the square root of y equals 1 over the square root of z. It's just a surprisingly simple and beautiful rule that connects all three of those circles perfectly. But hold on a second. You know, geometry is often full of surprises. Is this little circle really the only one that can perfectly kiss the other two and the line? And it turns out, no. There's a second solution. If you take the difference between those terms instead of the sum, you actually find the radius of a fourth circle, one that's so big it would enclose the first two. It's just a perfect example of this theorem's hidden depth.
Okay, so we've talked about the three circles, but there's a fourth element in that drawing that we've kind of been ignoring, and this is where things get really fascinating. So prepare yourself for a bit of a mind-bending twist.
I'm sure you've been wondering this whole time. Okay, fine, but what about the straight line at the bottom? All three circles are kissing it, so how does a straight line fit into a theorem that's all about circles?
And here is the big reveal, the crucial insight. Mathematically speaking, a straight line is just a circle with an infinite radius. I know, it sounds wild, but just imagine a circle so enormous, so massive that its curve looks totally flat to us. That's our line. It is the fourth kissing circle.
So what this all means is that our initial image isn't the whole story. It's actually a special case of a much bigger, more general theorem that describes the relationship between any four kissing circles, no matter what their size is.
And what's truly amazing is that this beautiful geometric idea isn't just found in European mathematics. A very similar fascination with this exact pattern showed up completely independently, half a world away.
The general theorem looks at something called the curvature of the circles, which is really just a simple idea, 1 divided by the radius. So a tiny circle has a high curvature, and a huge circle has a very low one. What is absolutely incredible is that this same puzzle was being explored in traditional Japanese mathematics in an art form known as sangaku. These were these beautifully illustrated wooden tablets that presented geometry problems not as homework, but as artistic offerings hung in temples. It had universal harmony, discovered by different cultures in their own way.
So, what started as a simple drawing of some circles on a line turned out to be a window into this incredibly deep and elegant mathematical rule. A perfect, beautiful relationship, hiding in plain sight the entire time. And that really leaves you with a final thought, doesn't it? If a rule this beautiful can govern something as simple as a few touching circles, what other elegant, hidden patterns are just out there, waiting to be discovered in the world all around us?